So in this video, we will look at the next example 5.14a. So we need to find the surface integral for the vector field given. So we have only ing, where the surface that we have here is over the surface ABCD. So as we know that, okay, let's say now you have this unit cube. What is the meaning of unit cube? It is a cube. What is different cube and cuboid? So cuboid, the measurement for the length, width, and the height maybe not the same, but for cube, they should be the same. The length, the width, and the height. Okay, and unit means the value of them. They are equal to 1. So that unit cube. So now we know that this one, we only interested on finding the flux. Okay, the flux for the given when the fluid is passing through this solid. Sorry, not a solid, but passing through the surface A, B, C, D. Okay, so here the value for them. This is one. This one. What else? Yeah, 1. Okay. So now we want to find. Okay, remember I teach you before this. How can we evaluate the surface integral when we have the vector field? So in general, the surface integral is f dot n ds, where is a portion of the surface, where the surface here that we are interested to have is just this plane. This is a plane, right? A, B, C, D. So we have A, B, C, D, and the value of them is 1 because unit means 1. Okay, and what else that we have? We are given the vector function. So now you have to take note here. They give you ing. So 2y plus z, and for component y you have -2. So now the k component 0. You can put 0 or you can just have this one. Okay, so now we want to solve the surface integral using a new form, which is more simpler to work with, f dot n dA. So when you have the dA, you transform the unit normal to the normal here, and automatically you have dA, and it is over the region. Okay, so now the question is, what is n? So how can you get n? N is a normal vector to the surface. So you can see here the surface ABCD is part of the solid cube. So obviously, when you said that n or a normal vector or unit normal vector always point outward to the surface, that is the orientable surface, right? Orientable surface always point outward. So imagine this is a cube, and you have this surface ABCD. So what is the direction of n, or unit normal or normal, that we have, so that the flow is always point outward to the surface? Okay, imagine this is a cube, a box, and then what is the direction, so that you can say the flow is, or the n, the normal vector, always point outward to the surface if this one is a cube. So you will see that the direction, we have to put an arrow, right? So the direction should be, so this is your plane, your surface ABCD. It is a plane. So this is your So that is your surface. Okay, so the thing that we want, we say that it is point outward. So then the direction should be point to which direction? Outward. So that way, right? That way. Which is if normally we have okay, let's say they don't give you the labeling, so we understood that this one should be X, that we are using the standard orientation. So this is Y and this is Z. Okay, so your n or unit normal vector should be in this direction, and it is positive in this direction, where it is the opposite direction to the yeah, it's okay. I mean for that we have to look at the surface equation, and since the surface equation is not given, then you have to find it. Okay, so if you look at from the sketching here, so what is the equation for this plane? If this is X, so this is the front wall, right? Remember, I always mention to you, if you have the this standard orientation, so this wall is called front wall, and this wall is called left wall, and down here is called the floor. Remember that? So for the front wall, what is the equation of this surface? So that one's supposed to be, what is the equation? If this is X, so it is located at X equal to 0. So we call this as X0. So this one, we call this as X equal to 0 plane. Okay, so X equal to 0, remember, if you think about 2D, it is a line. But if you think about 3D, and it is a plane, where it is a plane which is located on over here, which is a front wall. Okay, so this is X equal to 0. So now, in obtaining, so the question is, we are looking for the normal vector, okay, where the direction is in this direction. So now, how can we get that? We get that, so it's basically from, you have to find out the gradient phi. In order to get the gradient phi, you have to get the phi first. How can you get the phi? So now the question here is, how can you get the phi? So to get the phi, you have to refer to your information regarding the surface function or equation. Okay, so we know that the surface is this plane, where this one is the equation of this plane, or the function of this plane is X equal to 0. Okay, so that is the equation, simple. In this case, we only have X equal to 0. So then we have to accept that one to be a function or equation. So now we can see that. So now the surface function, that from the given sketching here, it is X equal to 0. So now you have to remember, I told you there are three cases where X is the function of, if you have X equal to, so X is the function of what? Z. No, YZ, right? If Y is the function equal to, so you have Y is the function of XZ. But if you have Z equal to, so you can say that the function is in terms of XY. So in this case, you only have X equal to 0. So in general, we can say this is the a type of equation of the function of YZ. Do you agree with that? Okay. So now, based on the standard, please refer to the previous video or my notes. So if you have actually this is the first step, determine the type of the equation that you have. So now we have this, so we know that our region should be on YZ plane. Okay, now you can see your region is a square, right? A square, which is this one. That is your region, where the value of them is 1, 1. Okay, so that is your region. So meaning that now the question is, how can we get the phi? Where your phi should be is the function of Y and Z. Do you remember how to get phi? So you have to bring to get phi, so x minus whatever equation or expression that you have on the right side, and you have equal to 0. So in this case, your f, okay, x is equal to 0, so your f here is 0, so you have x minus 0, sorry, yeah, x minus 0 equal to 0. So then your phi is just x, okay, because you can see here the equation itself already 0 equal to 0, so we accept this one to be phi. Or if you don't understand that, just remember in the very basic one, you have x equal to f is the function of yz, so then you have to make it equal to 0 and bring everything to the left, and you will get this, because f here from the given, from this example, x is equal to 0, your function here is 0, so x minus 0 equal to 0, and it is x, just x. Okay, so now our phi is x. So we want to get the gradient phi. So you have phi x, phi y, phi z. Then differentiate x with respect to x. You got 1 and the rest you get 0. Okay, so it is okay. If maybe you might wonder, just now I write down the f just ing, but you can put extra, okay, doesn't matter, you can just put 0, or you can just ignore that, because after that when you differentiate them, you apply the dot product, so 0 multiplied by 0 and end up to be 0 as well. Okay, so that is your gradient phi. But remember I mentioned before, from the gradient phi, but it can be positive gradient phi or negative gradient phi. So then you have to decide which is which, this one or this one. So now how can you determine the correct end, whether positive or negative gradient phi? You have to look at from the sketching, and in this case the sketching is given, so you can see this one as your region, where your region in this case lying on y and zy plane, ZY plane, and it should be matched with this one. Okay, should be matched with this. So if you put here, let's say x, maybe xy for example, but this one zy, so it's look, you did something incorrectly, then you have to double check. Okay, so now the region, we have a constant here, 1, 1. We have a rectangular region, so meaning that the limit of y and z, they are all constant. That is about the triple integral, the double integral that we have to face after this. But now we want to determine the end first. So as you can see here, as we decided just now, our end should be in this direction and it is positive. So if this is the direction where the end is positive, so we can see that the direction here is always point to negative x, right? Negative area of x, negative value of x. So meaning that in this case, we should have in our gradient phi, the component. Okay, now asking yourself which component that we have to focus here. So since we have x here, so we have to focus on the I or x component. So now for this one, for your gradient phi, you have to make sure that your component I should be negative, because opposite direction to the positive x, so the component I should be negative. So now by looking at your result here, it is positive, right? So meaning that we have to make sure that the gradient, the component I here should be negative. So how can we make it negative? So to make it negative, we just multiply all of the gradient phi to -1. So now it's become -1, 0, 0. Then this is your end. Okay, so now that is your end. So now we already got our end. Okay, so now we okay, After you manage to get the n, then you have to proceed to the next level, to the next step, where finding the dot product between f and the n that you obtain. So this is our n, and just now our f is 2y plus z and y minus 2, 0. Okay, and when we apply the dot product f and normal vector, so we have negative 1 multiplied by 2y plus z, and the rest are 0. So 0 multiplied by minus 1, 0, 0 multiplied by 0, 0, and we got negative 2y minus z. So then we plug in our dot product there. Okay, I write here. So f dot n dA R, the region is lying on YZ plane, now becomes minus 2y minus z dA over the region, where the region lying on YZ plane. Okay, so now we managed to convert from surface integral into the standard of double integral. Okay, remember I mentioned before the surface integral is the generalized form of double integral. So after you apply some process finding the n, then you can obtain the specific double integral like this. Okay, so the next is you have to integrate, but before you integrate, you have to check your integrand. You should check the possible variable that you can have. Okay, according to your choice just now, where your x is a function of yz, so the possible or the possible variable allowed to be the integrand or to be in this expression only y and z. You cannot have x. Okay, so since now we already have, or you can just check here. So that's why I always put our region lying on YZ, because this one will always guide me to just directly check whether I have the correct integrand or I have to change. So now you can see here our region on Y and Z. So the possible variable that are allowed is only Y and Z. Only Y or only Z or only Y and Z. No, there is no X. Okay, so now it looks like we have no problem here. So then we can proceed to find the order of integration and also the limit. Okay, so since our region here is just a rectangular region, and it looks like our integrand is quite simple, right? In order for us to integrate for respect to y or z first, so we can choose any of them. Which one you want to use? Any. Okay, so dy, dz. So now because it is a rectangle, so the limit are all constant. So z 0 to 1, y also 0 to 1. Then we can integrate that. Okay, so I think we have no problem to integrate this. Okay, so then when we integrate, and this is the answer. Okay, so the next is example 5.15. So let's the surface is the sphere with radius a. So imagine you have a sphere with radius a. So okay, and this one A, this one A, this one A, Z, X, Y. So you have to evaluate the surface integral where the vector field available around sphere here is given by zk, which is 0, 0, z. Okay, so now when we are talking about the surface, so the surface, so what is the surface equation? So in this case, the surface equation that we have is given by, from the sphere, x squared plus y squared plus z squared a squared. Okay, so now you have to first and foremost, you have to decide what type of equation of the surface that you have. Okay, where x is the function, or x equal to, y equal to, or z equal to. Okay, so let's say because we always have, you can have x equal to, y equal to, or z equal to. So in this case, I decided to have z equal to. So when we rearrange that, we need only z, not z squared. Okay, so now look at the equation of z. Positive, negative. So meaning that in this case, you have two different surfaces where, okay, I give that as sigma 1. Okay, the surface now is split into two surfaces, sigma 1, sigma 2. What is a sigma 1? The sigma 1 is coming from the positive square root while the sigma 2 is coming from the negative square root. Okay, so meaning that if you want to provide your surface integral f dot n, yes, sigma, and since the equation here, they are different, one is positive, one is negative square root, it looks like you have to split your calculation into two calculations, where the first one, your surface integral, where your sigma, your surface is when z is positive, given by z equal to positive square root. And the other one is coming from the other half of the surface, where given by sigma 2, where is the surface equation is negative a square minus x square minus y square. F dot, we use the standard one first, ds. Okay, so now it looks like the calculation, okay, if you done this, it may take some steps and you got the answer. And after that, you have to repeat the same calculation, but just modify from positive square root to be negative square root. So the pattern of the expression should be more or less the same, but just different sign, and end up you get another value, and at the end of the solution you have to total them up. So it looks like your work becomes double, right? You have to calculate twice for the surface integral. Okay, so I'm not going to show this in detail. Okay, maybe I just compute for the sigma 1. Okay, so now meaning that we want to do this part. Okay, only this part I want to show you how complex it is. Okay, so for this we have to find the n, a normal vector to this surface. Okay, but from the sketching, which one is the sigma 1 and which one is the sigma 2? Which one? Sigma 1 is positive z, which is the upper, okay, the upper part of the sphere, which is just hemisphere where z is positive. This one. Only this surface. Up here. This one and this one. Okay, hemisphere where z is positive. That is sigma 1. That is sigma 2. Sorry, sigma 1. How about the sigma 2? Sigma 2 is another hemisphere, which is down part, the lower part of the sphere. So this one is given by, or we call that as sigma 2. And then because the question here asking for the whole surface, the whole sphere, then that's why you need to total them up. Just imagine, remember I told you the physical meaning of, one of the physical meaning of this calculation of the surface function where f is a vector function. Actually we are computing the flux. So imagine now you are computing the flux where the fluid flow using this surface, the whole sphere. Okay, but because of you have a different equation, sigma 1 we give you positive square root, and the sigma 2 will give you negative square root, then we have to split the calculation. Okay, but end up you have to total them up after you got the solution. So now I want to settle down for the positive z. So now we want to obtain the n. So in this case, so the first one you have to decide what is the equation that we have. So z is given by square root of a square minus x square minus y square. So in this case, we can see that z is the function of x and y. So what is the phi for this? So the phi is, sorry, it is not vector. It is not a vector. Just a equation, the scalar equation, scalar function. So z minus f xy and equal to 0. So we have z minus square root a square minus x square minus y square. Okay, so now we obtain the gradient phi. Okay, where we have phi x, we have phi y, we have phi z. This is not Q. Sorry about that. Phi. Okay, so differentiate the equation here with respect to x. So maybe I have to rearrange this to be z minus a square minus x square minus y square to the power of 1 over 2. So when you differentiate with respect to x, okay, now for phi x, okay, I'll show you the phi x first. So differentiate, so z is 0, negative 1 over 2 a square minus x square minus y square to the power of minus half, multiplied by the derivative of the inner function with respect to x, you have minus 2x. So negative cancel, 2 cancel, so you have x over a square minus x square minus y square square root. So that is your first. Okay, because it is quite a long expression, so I have to rewrite here. So the first one, x over square root of a square minus x square minus y square. Now we want to see how about phi y. Phi y. So z0 negative 1 over 2 a square minus x square minus y square to the power of negative half, multiplied by the derivative of the inner function with respect to y, got minus 2y. So negative cancel, 2 cancel, so you got y over the square root of a square minus x square minus y square. So that is 1 over square root a square minus x square minus y square. And z, okay, you want to differentiate respect to z, and z is only over here, and the rest are 0 when you differentiate respect to z, right? So the answer here is 1. So your 5, 1. Okay, so now based on your sketching, you have a closed surface, right? Now we are talking about the n, the direction of n, or unit normal, normal or unit normal. So we want to have the orientable direction, which is that always point outward to the surface. So this is your surface. Your surface in red is part of the closed surface, just like the cube that we have just now. So when you see that the n should be point upward to the sphere, specifically where your surface is over here. So now what is the direction of n, so that we can say always point upward to the sigma 1. Okay, so for that, this is just, I erase that, I don't want you to get confused. So now what is the direction? So the direction that you have to provide is point outward. That is called outward. That is called outward. That is called outward. And over here is quite hard for me to sketch because we can't see that in 3D, right? So that's why I always choose this one, this one. Okay, so from the arrows that we provided, so now you have to determine the component I, J, or K, positive or negative. It looks like okay, so since we don't want to get confused, then we have to go back with our function type. This one. You have z equal to, meaning that we only want to focus on the component of k. We only want to focus on component k. So now k, which is z, right? Z exists. Okay, so now from the arrow that we provided here, which is point outward to the surface sigma 1, which is the red one here, always point to z positive, always up here, the direction, never going down, right? Up here. So we want k always positive. You have to write it down. Okay, write it down. It is not part of the mark, not part of the answer scheme, but then just to guide you. Otherwise, it's just easy for you to get confused. So just write it down. We want k to be positive. Now you check your gradient. What is your gradient just now? Your gradient here. So just focus on the k component. Where is it? This one. We want it at top here, up here. We decided to have k positive. Now we check. Is it positive? Yes, it is positive. So we accept this to be our n, because it is already positive. We don't bother about the sign for any other components, component z or k. It is already positive, and this is our n. So now we obtain the from this one, so we can obtain the f dot. So for sigma 1, now the surface integral becomes f dot n dA over the region. So your region just now is on xy plane. Why? Because we decided to have this particular equation of the surface for sigma 1. So this one for sigma 1. Okay, so now we want to obtain the f dot n. F dot n, so this is your n. So what is your f just now? Your f given from the equation, we have 0, 0, 0, 0, z, right? 0, 0, z. So when you apply the f dot n dA, just ignore the dA first, just f dot n. So you multiply these two, so 0 plus 0 plus z. So you only have z. f dot n is z. Okay, so then you replace into your double integral. You have z dA over the region xy. Before we proceed to find to okay, now it looks like we are in the form of a specific double integral, right, over the region, and the region is on xy plane. But then you have to check the integral here. Is it possible? What I mean by possible, so your possible integral only in terms of x, or only in terms of y, or it can be in terms of x and y, but not z at all. But here you have z, meaning that you have to change. You cannot directly use the z. How can you change that? So you have to use this equation back. So z equal to, then you have to plug in this one instead of just z, because z is not allowed. You are only allowed x and y. So you have to replace z is this positive square root is a minus just now a squared. Okay, a squared minus x squared minus y squared dA over the region xy. So now we look at the region. Okay, what is the region? So imagine now your region, your sigma 1 is only the right one. So for this particular surface, which is hemisphere, and since we know that the region is only on the xy, what you can see on xy, what is the shadow when you are standing over here? Okay, some students call that as a shadow. So in mathematics, that is called region. Okay, but it's okay, it doesn't matter. We don't bother about the term. Okay, so when you're looking down, what is the dominant curve or the dominant shadow that you can see from the above? So you can see the circle with radius a, isn't it? So you can see the circle lying on y-axis plane with radius a. Okay, so then since it is a circle, so it looks like, and it is double integral, then it's more easier for us to solve this using polar. Okay, now we convert into polar. So a square minus r square dot r d theta. Your theta 0 to pi and your r is 0 to a. Okay, so this is the double integral that you have learned previously. Alright, so now you can solve this. I think it's not so complicated. You can use the direct substitution. U equal to a square minus r square. So du over du dr. Du dr, yes, minus 2r, and dr is du dr is du negative 2r. So you have dot r, and dr is du divided by minus 2 r d theta. Cancel. Okay, so you have negative 1 over 2. You have du d theta, negative 1 over 2. Now we integrate. You will get u 3 over 2, 3 over 2, 2 over 3 d theta. And then complete. Yep, okay, we have to replace back. So the surface integral for the sigma 1 for the top hemisphere, the z positive, is 2 pi over 3a cubed, the same as this one. Okay, now I don't want to Not because of I'm so lazy, but I just want to give you a chance to try yourself, for you to try yourself, because you just need to change the plus minus sign, and end up the answer is the same. Okay, and do you know why we have the same here? That is because of it is a sphere, because we know that the sphere has a symmetrical property, and you cut into two pieces, right? First half and the other half, where the size of this particular surface is the same. Okay, so that's why the answer is the same. Okay, please try yourself. Please try to find out yourself for this particular surface, and the process is exactly the same like this, but just change the plus minus sign. Okay, and the limit also the same. Okay, the limit also the same, where because of your region is the same. You have the same region, so that your limit will be the same. Maybe the different one is your n just plus minus sign. Why? Because of, okay, now look at the sigma 2. Now we are thinking about the direction of n. Always point outward to the surface green, the green surface here. So point outward this way, this way, this way, this way, and of course you have z is the function of xy. So for this, your z is negative, right? So you have to only focus on the component. Okay, so according to your direction here, and point outward to the surface. When the k is always negative, the z value always, the direction, the arrow here always point to the negative of z down here. So you have to have the k component. When you compute the gradient phi, you have to make sure your sign, we don't bother about the value, but we are only bordering on the sign. We need the sign of the k component, it is negative. Okay, and then that is only the difference for this particular sigma 2. And at the end, you have to total them up. Okay. So according to your first calculation to get the surface integral for sigma 1, then you can see that the calculation is a bit not so complicated, but a bit longer. Actually, for your information, but then the problem is you have to compute twice. This is for sigma 1, and you have to provide another sigma 2, the calculation for sigma 2. So your work become double. So I would say that it is a bit you're wasting your time. Actually, for your information, for the closed surface, so this one we consider as a closed surface. Okay, closed surface. You are talking about surface integral, and your surface is closed. Just now, for the previous examples, I give you all open surface. Even though you have, just like this one, even though you have a cube like this, but the surface that you are computing only A, B, C, D. So it is still considered open because we only have A, B, C, D. So this one is still considered open, where A, B, C, D is part of the cube, only this one. But in for this particular example, we have the overall sphere. Okay, so overall sphere, where we know that sphere is closed surface. So for closed surface, you can simplify your calculation for the surface integral using a specific theorem, where it is called as the Stokes theorem. Gauss theorem. Okay, where I will show you on the next video, and we will use a new notes which is about the Gauss theorem. So Gauss theorem is the way to help you to simplify your calculation. Okay, otherwise you have to waste your time to compute many surface integral. For example, if I ask you to compute the whole surfaces for the cube, so imagine how many surface integral that you have to provide. It depends on the number of surfaces that you have. So look at the cube here. So you have a cube. So when you have a cube, and let's count how many surfaces that we have for the cube, which is, it is a closed cube or cuboid. It is considered a closed. So let's count how many surfaces. So front here 1, back here 2, the right side here 3, and the left side here 4, and the top here is 5, and the down here is 6. So imagine if I ask you to compute the surface integral for the cube, the whole cube. So you have to provide me, this is for surface number 1, and you have to provide surface number 2. You have to provide the surface integral for number 2, number 3, number 4. Then you have to provide me 6 calculations for different surfaces. And at the end of your calculation, you have to total them up. So now you can see how much time that you have to waste. Because what I'm saying, you're wasting the time, because actually we have a more simpler simpler method to compute the surface integral for closed surface. So for closed surface, because this one is a closed surface. Okay, so I will show you about that, about the Gauss theorem, on the next video. Oh yeah, I should mention just now, when we have a closed surface, so it should be related to solid. So let's say they ask you to compute the surface integral for the whole solid, the surfaces for the whole solid. So then you have to compute the surface integral for the specific surface which are covering the solid. Okay.